All right, testing just a couple things. I'll get started in just a minute or two. All right, I think I'll go ahead and get started. So this is a review of related rates, which is a part of something you learn in Calc 1. Basically, the idea is connecting derivatives to real life scenarios. Basically, we're interested in rates of change. We're going to, because that's what a derivative is, a rate of change. So we're going to try and find a rate of change given a number of constraints. And it'll all kind of just come together once we use our knowledge of derivatives and the chain rule. All right, so here's problem 1. You dip your big toe into a large swimming pool, creating a ripple on the surface of the water that travels at 3 inches per second. We're assuming it starts, dead center, and it makes a perfect circle going outwards. So assuming the ripple creates a circular area whose radius is increasing at a rate of 3 inches per second, find the rate at which the area of the ripple is increasing after 12 seconds. All right, so with most of these problems, basically what you want to lay out is all the information that you know. That's part 2, actually, listed down here. You also want to know all the important equations that are relevant to the problem. So in this case, it's a pretty simple example. We're just working with the area of a circle. So what we're going to do is, so that's kind of our important equation. So we have A equals pi r squared. So that's our important equation. There we go. All right. So our important equation is the area of the circle, which is pi r squared. And in this case, we're given a rate. The rate that we're given is, let's see, we'll draw a little arrow over here. We'll say we're given the rate of change of the radius with respect to time. So we'll call that dr over dt. And that is 3 inches per second. So that's the rate at which the radius of the ripple is increasing. So we're also kind of given another quantity which is kind of hidden. So we're interested in the rate of change of dr over dt at time 12. So we actually know that our radius, which we can call r of t, is a function of time, which is to say, the radius is directly correlated to the time that has elapsed. So in this case, we evaluate t at 12, and since we're increasing our radius at 3 inches per second, and we have 12 seconds, so r of t is equal to 3 times 12, which is 36. All right. So we're given our dr dt, and what we're actually trying to find, it's at that last part of the question, the rate at which the area of the ripple is increasing. So we know at what rate the radius is increasing, but we don't know the rate at which the area is increasing. So the rate at which the area is increasing with respect to time would be written dA, where big A is area, over dt. All right, so we'll go back through 1, 2, and 3 real quick here. So the important equation is A equals pi r squared, the area of the circle. We are given the rate at which the radius is increasing, which is 3 inches per second. And then we're actually given, with a little bit of work, we're given the radius at time t, which is 12 in this case, which is 36. All right, so once we have what we're seeking, we'll go back to our important equation, and we'll start with that, because the best way to find dA over dt is to just take that A equals pi r squared and take a derivative, or differentiate it rather, with respect to t, because on the left side of our equation, that will give us dA over dt, which is what we're trying to find. All right, so we have A equals pi r squared. So we'll go ahead and just differentiate it. So it's a real straightforward problem for this first example. So we get dA over dt on the left side of our equation, and on the right side of the equation, pi is kind of like a constant, so we can pull it out. And then with r squared, we actually want to do a chain rule. So we'll do the exponent, which is 2, times the derivative of the inside, which is just r, and then we're left also with dr over dt. All right, so from here we can plug in a couple things, and our answer should be straightforward from there. So dA over dt equals, well, we found our radius, r, which was 36, so we'll get pi times 2 times 36. And then we also know our rate of change, since it was constant, it's 3 inches per second, so times 3. So we multiply all this together. Let's see. Do I have a calculator handy? Here it is. All right. I guess it's just 6 cubed, but 6 times 36 is 216. So we'll scroll down a little bit. dA over dt equals 216 times pi. So we know that the area of our ripple is increasing at a rate of 216, I guess that would be square inches times pi per second. And one thing that's kind of important with all of our related rates problems is, well, you can actually check your work with dimensional analysis, which is to say, so dA over dt, just that expression, should be, since area is a squared length, it should be an r squared over our unit of time, so t. So the left side of the equation here is length squared over time. And on the right side, if you look right up here, So even after we took the derivative, we had r, and we had dr over dt. So we have two r's, so squared length over t. So we know our dimensions are correct, so we did this correctly. All right, so that's example 1. We'll go on to another kind of easy example. Let's see. You bring a 1 square foot block of cheese to a party to share with your friends. You notice after 1 hour that the height, width, and length of your cheese has decreased by 1 inch. Assuming the length of each side decreases by the same amount each hour, how fast is the volume of your cheese block decreasing after 6 hours? So something kind of conceptually you can put together here. How the rate of change of the volume is going to be drastically different than the rate of change of the length of each side. If you have a 1 square inch, not foot, 1 square inch block of cheese, and after an hour, the rate at which the cheese is vanishing is negative 1 inch per second. With just 1 square inch, it would be gone in an hour. But obviously, when we have 1 square foot, so it would be 12 square cube, 1 cubic foot. Dimensions are important, people. One cubic foot of cheese. If you have like a 12 cubic inches of cheese, and you shave 1 inch off of each side, you're still going to be left with a lot of cheese, relatively speaking. All right, so just if we go to part 1 here, important equations. Again, it's a pretty simple example. The volume of a cube, we'll put V. Oops. We'll put V equals, we'll just say L is the length of the side. Since it's a perfect cube, it's cubed. So the volume is the length cubed. So what all are we given? So we're given an initial size of 12. Does that help us? Let's see. Because we're actually mostly interested at the 6-hour point. So we're actually not really too interested in the initial size. Basically, what we're supposed to just deduce from this problem is that once 6 hours have passed, it's rather than being 12 by 12 by 12, we are now at 6 by 6 by 6 because it's been 6 hours. You're taking off 1 inch every hour, so we're left with 6 cubed for our initial volume. So I guess we have an initial volume. So V of 6 equals 216. Let's see, L, each L is equal to 6, and I think that's just about everything we're given. Kind of the important thing, the derivative, the rate of change. So let's see, the rate of change is the length that we're looking at. So it would be dl. Let's try that one more time. So we have dl over dt, which represents the change of the length of each side with respect to the time. That is -1. And the units for that are inches per second. All right. And what we are seeking, let's see, how fast is the volume of your cheese? Okay. So we are seeking the rate of change of the volume. So not the length, we want the volume. So that would be dv over dt equals what? All right, so we'll go ahead and start with our important equation, which in this case is just the volume equation. So we have V equals L cubed, and we are interested in dv dt. So we'll just go ahead and take a derivative with respect to time. So our V L cubed will become dv over dt equals, so we'll go ahead and do a chain rule. So we'll get 3L squared times dl over dt. All right, and then from here we pretty much just plug in what we know. So we're looking at the point at which t is 6. We evaluate the length at 6 hours, which would be 6. So dv over dt equals 3 times 6, and since it's squared, times 6. And then we also have our rate of change of the length of each side, which is -1. All right. And then we'll just multiply that all together. And we have dv over dt equals -108. And since it's a volume, it should be inches cubed per second. All right, and we can always double check that if we go back to this equation up here. We see that on the left side we have a d volume over dt, so that would be a length cubed over a time. And on the right hand side we have dl over dt, which is a length over time, and we have L squared. So we have 3 factors of L in the numerator, a factor of t in the denominator, so we know that our units are correct in inches cubed per second. All right, now for a little more advanced of a problem. Let's see here. All right, we have a plane 8 miles high in the sky, and it's flying directly over us. It's currently 12 miles from where we're standing. The distance between you and the plane is decreasing at a rate of 200 miles per hour. How fast is the plane traveling? All right, so luckily we have a little picture here to help us out. But generally with these problems, you want to draw a picture just to visualize it and kind of get a better understanding of it. For this one, it's kind of vague as to what's going on. So I'll go ahead and make it a little bit more clear. So this is where we're standing. We're standing down here. And the plane, I'll draw my little plane, is right up there. So it's flying up over us. It's going that direction because it's going towards us. All right. So something that's not obvious from just the text here, we're actually dealing with a right triangle, which means our important equation is going to be a Pythagorean theorem. So a squared plus b squared equals c squared. All right. Let's see. So we have the given amount of how high the plane is in the sky is 8. We're given it's 12 miles from us, so that would be the hypotenuse. So let's see. So we're given distance between the plane. Let's call that c. So just for clarity, c equals 12. We'll say b equals 8. And then we kind of have x as an unknown, but we can just use Pythagorean theorem to calculate that real quick. So 144 minus 64 equals 80. So we have a equals square root of 80. All right, so that would be x, I guess. A equals x. I'll denote that over here just in case it's confusing. All right, so we also have, let's see, the distance between you and the plane is decreasing at a rate of 200 miles per hour. So that would be this 12, so that'd be c. So we'll go ahead, we actually do have a rate. So we have dc over dt equals, since it's coming towards us, the length is decreasing, so we'll make sure it's a negative. So we have negative 200 miles per hour. All right. So our important equation is Pythagorean theorem. We're given the distance between us and the plane, which is c. We're given the height of the plane. We weren't really given it, but we were easily able to deduce the distance, just the raw distance on the ground from us in the plane, which was root 80. And we want to find, oh no, I'm sorry, we're given also the distance, the rate at which the distance between us and the plane is decreasing. And let's see, so we're interested in how fast the plane is traveling. So that's not our vertical dimension, that's not B. It's not C because we're given that. That would be a really easy problem if we're just given it. So we kind of know that dA over dt has to be what we're seeking. So what we are seeking, it is dA over dt. And that just makes sense because the plane is, it's flying parallel to the ground, hopefully. Hopefully it's flying parallel to the ground. But that's what we're interested in. That'll give us that raw speed with just the horizontal component to it. All right. Let's see. So we might have to do a couple chain rules here. All right. So we have a squared plus b squared equals c squared. All right, we'll go ahead and take a derivative with respect to time. So that would be, let's see, so we have to do quite a few chain rules. So first we'll get 2a times dA over dt. And we'll get plus 2b dB over dt. And that is equal to 2c dc over dt. All right, so here's where we have to use our big brain thinking, or rather, a little bit of big brain thinking, a little bit of assumption. So we are kind of assuming that the rate at which the plane is getting closer to the ground is not changing. So we're assuming it is staying, far in the air, far from us. And what that means is that dB is actually 0. Or rather, dB over dt, the rate at which b is changing, is 0 because we're assuming that it's staying as high in the ground, same altitude. It's keeping the same altitude. That's the word to use. So we can actually basically just completely negate that whole term. So we're just left with 2a times dA over dt equals 2c times dc over dt. All right, so we'll go ahead and plug in a couple things that we know. So we know that a is root of 80. So we'll have 2 root 80. We're trying to find dA dt, so we'll leave that as it is, dA over dt. Let's see, we have c. C is also given. It's 12, and twice 12 is 24. And then the rate at which c is changing is also given to us. It's 200 miles per hour, and it's negative since it's coming towards us. So go negative 200 miles per hour. All right, so we'll clean up a couple things, just do some algebra. First, we'll just divide by 2 times root 80, and we'll completely isolate our dA over dt. So we have, oops, it's not area. dA over dt equals, let's see, I'll just punch some numbers in real quick. Let's see, be root 80 times, divided by, We'll divide by root 80. So let's see, we have negative 200 times 24 on the right side. We'll divide by 2, and we'll divide by root 80. And according to my calculations, we have negative 268.33 miles per hour. All right, so a couple things we can do just to make sure that the problem makes sense is, go back, look at the picture. Generally, since we're speaking, we're dealing with Pythagorean theorem. A squared plus b squared equals c squared. Any individual a squared or b squared is always going to be less than c squared. And since we were given since we're given the c is less than the change of a. And then we can also do dimensional analysis. There wasn't too much nuance with the units here. Up here we are given that whole equation is, each dA over dt is really just a distance over time. And distance over time plus a distance over time is still a distance over time. So on the bottom here we have distance over time equals distance over time. So we know that we did our units correctly. All right, go on to our next problem. Let's see. This is one of the more complicated problems you'll see. I'd say this is a staple problem of Calc 1 related rates. It's usually, filling up a swimming pool, filling up a cone, and we're going to get right down to it. All right, so you are filling a cone with water. The cone with the base side up is 8 feet tall, has a radius of 4. You're filling the cone with water at a rate of 9 square feet. I guess that should be cubed feet per minute. When the water level in the cone reaches 5 feet, how fast will the water level be increasing? All right, there's a lot to unpack here. Probably want to work quite a bit with a picture, but we will go ahead and establish our important equation first. And we're dealing with the volume of a cone. So we want a volume. We'll say that volume, it's the volume of a cone, which is pi r squared over 3 times the height of the cone. All right. So we'll draw a couple little things on our cone to make things more clear. So we have the center of the cone, and then we have a radius. Let's see, our radius of the whole cone is 4. And the height of the whole cone, so we'll go ahead and draw a little bar here, that is 8. Let's see, we're filling up the cone with a rate of 9 cubic feet per minute. And the water level in the cone reaches 5 feet, so we're interested in, let's say, about right there. So we're interested when, this is all filled with water down in here. So we'll draw another little bar. We'll say this is 5. All right. So let's see, we're given the height of the whole cone, which is 8. We're given the radius, which is 4. We'll actually only use that. We'll use that rather sparingly. It won't be in our final equation, but it'll help us figure out the volume that we're looking at, that we're trying to figure out the rate at which the volume is increasing, because the water level up here, when of the full cone relative to the full cone, is not actually increasing. It's increasing down here where the height is 5. So we actually want to find another radius here so we can calculate that volume. Let's see. So we'll go ahead and say we are given h which is 5 in this case. And the trick to this problem actually is, let's see, we'll draw a line here. And something you'll notice is that these all form, or rather this forms two right triangles. So we have, a large, let's draw a slightly straighter line. A large right triangle. Boom. Oops. And then we have a smaller right triangle inside it. And the height, so this is 5. This whole thing is 8. And then we have R and 4. So we're going to actually just use proportions to figure out that missing radius, which is to say that, let's see, 4 over 8 equals R over 5. So we see very obviously that the left-hand side of this is equal to 1/2. So half of 5 is 2.5. So we say that R is 2.5. All right. So we have this important equation, volume. We have height that we're given. We deduced our radius. And let's see. So we have a height, we have a radius, and we want to find how fast the water level is increasing. There's also one thing else that we are given, pretty important. The rate at which the volume of our cone is increasing. So we're interested in that smaller volume again. I'll note that. So we are given dV over dt. So dV over dt equals 9 cubic feet per minute. All right. And we are seeking how fast the water level is increasing. So the water level has to deal with the height, not the radius. The radius is increasing, but this problem just happens to be asking for the height. It is possible that a question would ask you how fast the radius is increasing, in which case we would do something slightly different. There's also another case where they'll ask you how fast the surface area of that bottom water level is increasing. And that would be, just another, kind of like another circle problem, basically, because we wouldn't be too concerned with the height. It would just go into our equation and kind of pump out a volume, or a value for us. All right, so we're given h, we've deduced r, we're given dv dt, and we are trying to find the rate at which the height is increasing. So we would say we are seeking dH over dt. Oops. So basically what we're going to have to do is we're going to have to use this equation up here that we have for the volume of our cone, and we want to get a dH over dt out of it. But the issue is that we have an R and a V. Well, the V isn't the issue, the R is the issue. So we'll have to go back and we'll actually have to substitute something in for this R so that we just get an equation in terms of V and H, and that'll make a lot more sense to us. Let's see. So we'll just go ahead and use proportions again. So we know that R is 2.5, H is 5. Basically the important part that we want to get from that isn't necessarily the values, it's basically just that R is 1/2 of H. So we know that R is 1/2 of H, so we'll go ahead and plug that into our volume problem, and that'll actually eliminate R as a variable that we'll have to deal with when we're differentiating. So we have V equals, we'll go ahead and bring those constants out, pi over 3, and we'll multiply that by R squared, and we substitute 1/2 H in for our R squared. So we'll get 1/4 H squared, and then we also have that other H, so times H. So it's really just H cubed here. All right. Make sure I have enough space to solve everything here, so I'll move everything over on the left. All right, so clean up things a little bit on the right side there. We get v equals pi over 12 times h cubed. And we'll go ahead and get right to the differentiation. So we have dv over dt equals, so again we bring out that constant of pi over 12, and then we'll do a chain rule. So we get 3 times h squared times dh over dt. All right. So now we have our dv dt, we have h, and we have dh over dt. So we basically have all the values that we need. We need to, well, we're trying to find dh over dt, so we'll go ahead and isolate that on one side of the equation. And we'll just need a little bit of algebra to do that. But first we'll go ahead and plug in all of our values. So dv over dt was the rate at which the volume was decreasing, or increasing rather, and that was 9 feet cubed. So we have 9 feet cubed over minutes equals pi over 12 times 3. Let's just go ahead and put 3 pi. Or rather, simplify it even more. 3 pi over 12 is just pi over 4. And then we have h squared. So now we have the rate at which we're trying to find isolated. Well, we don't have it isolated, but we have it in our equation. So we can go ahead and just plug in h. So we know that h is 5, so h squared is 25. Let's go ahead and put 25 right in there, and then that is feet squared. So we'll go ahead and do a little bit of dimensional analysis, kind of integrate into the problem here. And then we have that times dh over dt. All right, so then we'll go ahead and do some algebra, and we'll isolate our dh over dt. So dh over dt equals, so we would take 9 divided by 25. So 9 divided by 25 multiplied by 4, and then divide by pi. And we have a dh over dt of 0.23. And our rate that we're interested in, that we're looking at, is a rate of change of height over time. So in this case, we actually don't have that full length cubed over time like we did in the previous problem. So we actually, the thing we're trying to find is a length over time. So we want to look at our dimensional analysis, make sure that's correct. So the answer should be, it's increasing, so it's positive, so it's 0.23, and it should be feet over minutes, because it's a height that we're looking at, it's not the volume. So in this big equation that we did, oops, goodness. So this big equation, so what we did to isolate dh over dt was we had cubic feet per minute on the left-hand side of our equation, and we had feet squared times dh dt on the right-hand side of the equation. We divided by the units of squared feet. So on the left-hand side, instead of it being feet or cubic feet per minute, it actually changed down to feet per minute. So we divided by feet squared, we divided feet cubed by feet squared, and we just got feet. So a single dimension of length per minute. And we look in our answer, and that makes sense because we're looking at a length per minute. All right. Fortunately, that was all I had prepared, but let's see if we can squeeze something else in. Let's say we wanted to. Let's say we're given that that rate at which the height is increasing. Actually, I'm not sure if we even need that. We'll change this whole. We'll change this whole equation to be, or rather, the whole problem to be looking for the area of the circle. Since our circle is increasing, the surface area of the water is increasing. We'll try and find the rate at which that is increasing. Let's see if I can increase my opacity here. Or if I can just select a whole bunch of stuff and erase it. That doesn't seem to be an easy way to do that. All right. Well, I'll just go over it real quick. If we were trying to, if the question, instead of asking what was the rate at which the water level was increasing, it asked instead, what is the rate at which the radius of the water, or the water surface, is increasing? Instead of our important equation being volume, we would use what we would know from the surface area of a circle. So we would use A equals 2 pi r. And we actually just use our calculations for height to find what our r is. And we would solve it from there. So we would be interested in dA over dt. So let's see. So if we have dA over dt equals, and then we have 2 pi r squared. So we have 2 pi, and we do the chain rule. So there's another 2 times r, and times r over t. So actually we would need a little bit more information in this problem to actually figure it out. But hopefully, you only have to ever figure out one variable that's missing. So in this case, instead of the rate at which the cone is filling with water, we would be given either the rate at which the area is increasing and be asked to find the rate at which the radius is increasing, or we would be given the rate at which the radius is increasing and try and figure out the area, the rate at which the area is increasing. All right. So I'll just go back through everything real quick. Generally, related rates, more of the more complicated problems will involve volumes. And for that cone example, we'll scroll back down to there. The really important thing you want to get out of this is you have to use that the similar triangles equation to understand that we're actually given a lot more than just what's in that text initially. So we use that to find the radius, and we're only left with really one unknown, which happens to be dV over dh over dt. Let's see. So the little trick with problem 3 is really putting all the pieces together. The height or the altitude at which the plane is flying is not changing. That's very important when you get down to this equation. Draw a slightly better arrow. Boom. So the important thing to realize is the rate at which the altitude of the plane is changing is 0, because we're assuming that the plane is not changing in altitude. It's not getting any closer or further away from the ground. And that leaves us with just 2 unknowns in this equation down here. And since we are given the rate at which c is changing, we isolate dA over dt, and we're we find what we're seeking, the change, or rather the speed at which the plane is traveling. All right, so with the cheese example, I thought that one's kind of clever. Really, you're just looking at the volume. It's a pretty straightforward problem. You're looking at the volume of a cube, which is just length cubed, and really, as long as you have your differentiation down, just differentiate x cubed, which x is L in this case. Do a chain rule to get our dl over dt, and that's how we find the rate of change of the volume. All right. I guess I can add a little bit more detail to this first problem. So we are given, we're given a radius, r, and we have to evaluate that at t. So that's something important you want to realize is with these related rates problems, when it's asking for, a rate, in this case, the rate of change of the radius, you need to realize that we're interested in the radius at 12 seconds. So we need to evaluate the radius at 12 seconds. We can't just put in 3 for r, otherwise we're going to get a completely different answer. And that should make sense. It's for, we're looking at a rate of change after 12 seconds, and we're given that it's increasing at 3 inches per second, and it stays constant even for 12 seconds. All right, and this one, you just use that important equation that we use is the area of the circle, which is pi r squared. Shouldn't be anything too crazy complicated there, but we use a chain rule to differentiate r squared. We'll get it in terms of r times dr dt, and we just plug in values that we know of r and dr dt, and we'll find our area with respect to time. All right. I think that about wraps it up. I'll stick around, see if we have any questions from the stream. I'll do the best I can to try and answer them. All right, I think I cleared up a little bit of space. We'll try and tackle this problem from a little different approach. Clean up a couple more things real quick before I get started. Let's see. All right. So previously on this problem, we were given the rate at which the volume is increasing. So we were given dV over dt, and we were asked to find dh dt, where h is the height of the water. So let's say instead, so we still have a lot of the same things. Let's say instead we have, oops. So instead of trying to figure out how fast the water level increases, we're interested in how fast the area of the water surface is increasing. So that would require us to know how fast the radius is increasing. So let's say, we'll scribble this part out. We'll say we are given at the rate at which the radius is increasing is, let's see. So we found out that was 2.5. So let's say it's 0.5 feet per minute. All right. So again, we'll do our similar triangles. We have the cone is 8 feet tall, with a radius of 4. The point that we're looking at is when the height is 5 and the radius we found to be 2.5 by using similar triangles. Let's see, our important equation, previously it was involving volume, but we're actually not really too concerned with the volume. We're just really concerned with the surface area of the surface of the water. And in this case it's a circle since we're dealing with a cone. So again, we have A equals 2 pi r squared. Is that correct? Pi r squared. Getting a little ahead of myself. Pi r squared. Yeah, there we go. All right, so we are given r, which is 2.5. We're given dr over dt, which is 0.5 feet per minute. All right, and we are seeking the rate at which, we'll cross that out again. We want to figure out the rate at which the area is increasing of the water. So we are interested in dA over dt. All right, so we'll go ahead and go back to our important equation, which is A equals pi r squared. And we'll just differentiate it since we know we'll have a value for r, we'll have a value for dr over dt, and we'll get what we're seeking on the left-hand side, which is dA over dt. So dA over dt equals 2 pi, so I brought that 2 forward from the chain rule, kind of working ahead a little bit, and then we're left with r times dr over dt. All right, so we are going to go ahead and plug in our values for r and dr dt. So we know that r is 2.5, and we know that dr dt was 0.5. So move over here real quick. dA over dt equals 2 pi times 2.5 times 0.5, which is, really just a half, but we'll write it as 0.5 for the sake of consistency. All right, we don't want to forget our units because that helps us double check our work, make sure we did everything correctly. So 2.5, that is length. Since that was r, that was just a length, and then our 0.5 is our rate at which the radius is increasing. So that would be a length over a time 2.5 is a length, and then area is a length squared, and t is just t. All right, so both sides of the equation, L squared over t, L squared over t. So we'll just do some algebra and we'll pretty much get our answer straight away. This is a pretty straightforward version of the cone problem. So we have dA over dt equals 2 times 2.5, which is 5, and then times a half, so it'd just be 2.5 times pi. And that would be, well, I guess I can be more specific with my length. It's feet. Correct? Yes, it's feet per minute. All right, and that just kind of goes to show you that some of these problems can actually be kind of tricky. You need to know what you're doing when you set them up, because I just asked, I changed the problem very slightly, even though all the scribbles kind of make it look like I changed a lot. I actually just asked, what the rate at which the surface area, which is the area of a circle, is changing. Even though there's this whole cone drawing, what we're trying to find, our whole solution is completely different. So you really want to read those problems carefully and make sure you know what you're doing with a lot of these, because they can be tricky, and you see a triangle, you just start doing Pythagorean theorem, and you might be completely on the wrong path. All right, so I'll go ahead and call it there.